Okay, so now what I know, see, this is a sum of two squares minus 1. And this critical point, xy equals minus 1, 0, that's exactly when this is 0 and that is 0. So that's the smallest value. This is always greater or equal to 0, same with that one. So that's always at least minus 1, and minus 1 happens to be the value at the critical point. So it's a minimum. Okay? Now, of course, here I was very lucky. I mean, in general, I couldn't expect things to simplify that much. In fact, I cheated. I started from that, I expanded, and then that's how I got my example. Okay? So the general method will be a bit different, but you will see it will actually also involve completing squares, just there's more to it than what we've seen. Okay, so we'll come back to this tomorrow. Sorry? Oh, how do I know that this equals? Y is what negative 1? Sorry.
Like, how do you know that whole function is greater?
How do I know that that whole function is greater or equal to negative 1? Well, I wrote f of xy as something squared plus 2y squared minus 1. Okay? This squared is always a positive number, or non-negative. Right? It's a square. The square of something is always non-negative. Similarly, y squared is also always non-negative. So if you add something that's at least 0 plus something that's at least 0, and you subtract 1, you get always at least minus 1. And in fact, the only way that you can get minus 1 is if both of these guys are 0 at the same time. Okay? So that's how I get my minimum. So more about this tomorrow. So in fact, what I would like to tell you about now instead is a nice application of min-max problems that maybe you don't think of as a min-max problem, but you will see, because, I mean, you don't think of it that way, because probably your calculator can do it for you. Or if not, your computer can do it for you. But it's actually something where the theory is based on minimization in two variables. So very often in experimental sciences, you have to do something called least squares interpolation. And what is that about? Well, it's the idea that maybe you do some experiment and, you record some data. So you have some data X and some other data Y. And I don't know, maybe, for example, X is, maybe you're measuring frogs and you're trying to measure how big the frog leg is compared to the eyes of a frog or whatever, or, trying to measure something. And, if you're doing chemistry, then it could be, how much you put of some reactant and the output, how much of the output product that you wanted to synthesize is generated. All sorts of things. Make up your own example. But so, you measure basically for various values of X what the value of Y ends up being. And then, you would like to claim, oh, well, these points are kind of aligned. I mean, of course, to a mathematician, they're not aligned. But to an experimental scientist, that's evidence that there's a relation between the two. And so you want to claim, and, in your paper, you will actually draw a nice little line like that. See, these two functions depend linearly on each other. Okay? So the question is, how do we come up with that nice line that passes smack in the middle of the points? So the question is, given experimental data, xi, yi, so maybe I should actually be more precise. So you're given some experimental data. You have a data point x1, y1, x2, y2, and so on, xn, yn. The question would be, find the best fit line of the form y equals ax plus b that somehow approximates very well this data. So, you can also use that, by the way, to predict various things. For example, if you look at your new homework, actually the first problem asks you to predict how many iPods will be on this planet in 10 years. Okay? Looking at, past sales and how they behave. One thing, by the way, before you lose all the money you don't have yet, you cannot use that to predict the stock market, okay? So don't try to use that to make money. It doesn't work. So one tricky thing here that I want to draw your attention to is what are the unknowns here? So the natural answer would be to say, well, the unknowns are x and y. That's not actually the case. Okay? We are not trying to solve for some x and y. I mean, we have some values given to us, and when we are looking for that line, we don't really care about a particular value of x. What we care about is actually these coefficients a and b that will tell us what the relation is between x and y. So in fact, we are trying to solve for a and b that will give us the nicest possible line through these points. Okay, so the unknowns in our equations will have to be a and b, not x and y. Okay, so the question really is find the best A and B. And of course we have to decide what we mean by best. So best will mean that we minimize some function of A and B that measures the total error that we are making when we are choosing this line compared to the experimental data. So maybe roughly speaking, it should measure how far these points are from the line.